Okay, so I think we have everything figured out. For those of you who do not know me, my name is Professor Eric Davis. I'm going to be your instructor for this summer session of Thermo 2. Typically, we would have started class at 1:30 today, run from 1:30 to 2:45, 15-minute break, and then now starting at 3 p.m. and running until 4:15 p.m. That's Tuesday, Wednesday, Thursday, unless you hear otherwise. There is my email. That's my office. The TA is standing in the back of the room. That is Mark. Mark is awesome. Right, so don't upset Mark. Mark's hard to upset. So if Mark comes to me upset, then you've done something extremely wrong. Right? That's about it. I just wanted you to see Mark. Mark, I didn't put your office. What's your office number? It is, you said G30? Okay. Office hours. We will have office hours on Tuesday from 10:45 until 12:15 p.m. Those will be held in 107 Earl Hall. Mark will handle those office hours. If you want to meet with me for any reason, I suggest that you email me for an appointment. If my door is open, you can always stop by. But that doesn't mean that I will have time to help you. Okay? And along those lines, a little bit of etiquette when it comes to offices of faculty. So you walk up to an office, the office door is open. And what I typically see is a knock, a walk into the office. Hey, Professor Davis, da, 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 da. Right? Now just imagine you're at someone's house. You walk up to their front door is cracked, right? You don't really know this person, you just know where they live. And you knock on their front door and then you just walk into their house. Hey, how's it going, everyone? I'm so-and-so. Knocking on my door does not mean that I'm saying, come into my office, right? That is saying, hey, I'm here. Are you available for me to come into your office? Right? That is a general suggestion, right? For me, it's a practice, right? Do not knock or just walk into my office, right? I'm a super friendly person, but there are things that I am very, very particular about, right? I'm not going to come violate your space. Please do not come violate mine. Okay. I'm not going to go over too much here. Textbook. Looks like this. There's a lot more to it. This is just the cover. Luckily, it comes in a paperback form, so the cover easily rips off. Therefore, I can carry this around with me. All right, this is a required textbook for the course. All right, what do I mean by required? Well, I'm going to expect that you can pull information from this textbook. All right, if I say do this problem, I'm not going to write it out. If there's parameters that are in this textbook, right, I'm not going to just give them to you. You're going to have to go look them up. Does that mean that you need to physically own? Thank you, Mark. Does that mean that you need to physically own a copy of this textbook? That's up to you. I think it's a good idea, but again, that is totally up to you. There are some supplemental texts listed there. You are probably familiar with the first. I imagine that's the textbook that you use for Thermo 1, Elliott and Lyra. I hate Elliott and Lyra. That's why we do not use Elliott and Lyra for this course. We will refer to it occasionally. 5 and 6. 5 and 6 are important. They are the companion websites for the two textbooks. One, the required textbook, one Sam or Elliott and Lyra. You should be familiar with the number 6, because hopefully you use that in Thermo 1. If you're not, right? Please go to that website, become familiar with it. Right? There are a number of useful Excel spreadsheets that you can get from that website that will be helpful, right, in solving problems for this course. Same thing with the Sandler, I would say is probably less useful, right? Unless you are really good at Aspen or MathCAD or MATLAB. There are some Excel documents on there as well, but it's a bit more advanced. Attendance. I'm expecting you to come to class. The university says that I need to take attendance. So I've taken attendance. That's how I'm going to take attendance every single day. That's all I'm going to say. You're an adult. Refresher quiz. And we will have a refresher quiz that will occur on Wednesday, July 5th. That's 1 week from today. And it will cover material that you learned in 2200. Right? The quiz will take about 30 minutes, 25 to 30 minutes. We'll do that at the beginning of class, and then we'll continue the lecture. Right? What you will find on Canvas if I can get this to work. Is a review sheet for the refresher quiz. If you can go through and you feel comfortable with everything that you see on this document, which is about 22 items, then you should be fine for the refresher quiz. Problems will either be pulled directly from this, or there will be some variation of this, meaning number 22, that's a very specific example. If I gave you something like that again, it probably wouldn't be that exact example. It would just be something similar, right? But I may say, hey, write down any equations needed to describe the equilibrium state for pure ethane existing in vapor liquid equilibrium. That may just come straight from the study guide. So this is your ticket to getting a good grade on the refresher quiz, so that you take the refresher quiz seriously. Right? The refresher quiz is 5% of your overall grade. So refresher quiz, 5%. Homeworks, 10%. There will be an Aspen project, a group Aspen project. We'll talk about that next week, probably. You'll have 2 midterm exams, and then you'll have a final exam. You will see here my grading scale. If you get at least a 90, you get an A, at least an 80, you get a B, so on and so forth. Based on these percentages, you should be able to calculate your own grade. And so you should know whether or not you can get an A, B, C, D, or below a 60, an F in the course. Right, if you miss an exam because of some emergency, right, I need some written excuse for that, an official written excuse. Final exam, there's 2 suggested dates for the final exam. Friday, August 4th, Monday, August 7th. So what I'm going to do is on the first homework assignment, one of the problems is going to be a vote. You're going to vote for either one of those exam dates for the final. It's a democracy, and so majority wins. To give you some perspective, you may think, well, and I don't care what you choose. Let me start there. I don't care what you choose. Totally up to you, your life, your schedule, whatever you need. Right? It just may be that everyone else in the class doesn't need that, and so you end up having to sacrifice, but again, democracy. But what I will tell you is if you're looking at that and saying, well, if we delay it until Monday, then that's going to give us additional study time over the weekend. Yes, 100% agree with you. And I'm going to continue that thought, right? That's the first part of the thought. Second part of the thought. And then if questions come up, we're going to be able to email Professor Davis, and he's going to be able to help us answer those questions before the exam on Monday. No, that's not going to happen, right? So keep that in mind. If you want the extra time to study, yes. If you think that I will be checking my email on the weekend before the final exam to answer any last minute questions, that's all I can say. Okay. I say that because you're all adults, right? And I come off as terse, right? Blunt, sometimes aggressive. I don't need a microphone when I talk. That doesn't mean that I'm not a very nice and understanding person, right? But because I'm going to treat you as an adult, you have a deadline, and you know what that deadline is now. Start preparing for it, right? Everyone has things that pop up in their lives. You have things, I have things. I can't change those deadlines, right? They are what they are. Right? So please do not wait until the last minute to start studying and then be upset that I am somehow not as responsive to your frantic questions and emails as you may want me to be. Right? With that said, well, actually, I want to scroll down one more so we can nip this one in the butt. Scroll down, scroll down, scroll down, scroll down. That last bullet right there. The use of laptops or cell phones is not allowed in class. Right? If you have a laptop open right now, please close that laptop. If you have a tablet, right, I'm going to treat you like you do during takeoff. You cannot have the keyboard attachment to the tablet, but you are more than welcome to have the tablet out, right, to take notes. I understand. But please, no laptops, no cell phones. I'm not going to sit here and monitor. If you want to sit and text on your phone, that's fine. You paid for this course. If you want to show up and text during it, that's your prerogative. If I can tell that it is distracting or bothering other students, I will ask you to leave. All right? You getting up, walking out of class to text or take a phone call, coming back in, that will not bother my ability to lecture. Don't worry about that. Maybe consider your fellow classmates, right? But it's not going to bother me if you want to come in and out, if that's who you are. Probably sit in the back of the classroom so that you're not constantly doing that during the course. But again, if you want to walk in and out of the class 15 times during the lecture, I will be okay. All right. What was I going to say about that? Oh, I was talking about something about an email, right? No, there was something else. But we're going to circle back to emails. Okay. So when you go to send me an email, I want you to ask yourself one of two questions. The first question is, can the answer to my question be found in the syllabus? Second one is, can the answer to my question be found on Google? What do I mean? I want to clarify the second one. The second one means, let's just say I didn't put the final exam date here. Don't email me and ask me when the final exam is. There's an academic calendar. You can go online. You can Google that yourself. Hey, I didn't really understand your explanation of the first law of thermodynamics. That's something you could Google. That's not what I'm talking about. You can email me about that kind of stuff, right? Hey, what's the density of chloroform at 55? So all of this is to say, it costs me zero effort to not answer your email or read your email. So you can bombard me with emails as much as you want. In fact, I encourage you to, if you think that I am being unresponsive to something that I should be responsive to. Send me an email. If I haven't responded within 24 hours, send me another email. If I haven't responded within 24 hours, send me another email, etc. Right? But after the second or third one of those emails, if you take a step back and you say, that's probably information that's in the syllabus, or man, I could probably Google that. That's probably why I'm not answering your email, right? There are plenty of other reasons I'm not answering emails, which is why, again, it's not going to bother me if you said, hey, I sent you an email yesterday, you didn't respond. Hey, I've sent you 2 emails now, you didn't respond. That's fine, right? You should do that. You should expect that professors are horrible with emails, checking them, right? I'm associate chair, so it's even 10 times worse than that. So please email me as much as you feel the need to, but if your email falls within one of those 2 questions, that's more than likely why you're not getting a response. Homework. All right, homework, you can turn that in to me. There's going to be a cardboard box. It's going to sit outside my office. It's going to say CHE 33210 homeworks. All right, there's going to be a due date and a time. If your homework is not in that box, when I pick the box up or Mark picks the box up, it's late. Right? You get a 0. You can still turn it in. You can still have Mark work through it and grade it, but you will receive a 0 in it. 0 on it, excuse me. You can always turn things in early. Hey, it's due on Wednesday, but I'm done on Tuesday. The box isn't out there. Stop by my office. If it's open, give it to me in person. If it's closed, slide it under my door. Right? Things can always be done early. All of your homework, well, let me finish this one. Do not hand me homework assignments before or after class. Right? We're in the same building. So you're saying, here, Professor Davis, you carry this up the stairs and put it in your office because I don't want to walk up the stairs and slide it under your door. No. Okay. Homework format, engineering paper or computer paper. I don't care if you go buy the expensive green engineering paper that they force down your throat in freshman engineering. What you do is you just go online, you get an image of engineering paper, you copy it into a Word document, and then you print that out. Now you have engineering paper. Beautiful. The only type of paper that I will not accept homework on is notebook paper. Right? Do not turn your homework assignments in on notebook paper. Right? If for some reason you have an issue obtaining engineering paper or blank computer paper, right, please come talk to me. Right? But do not turn in homeworks on notebook paper. Those will also get 0s. All right. The last thing that's important with homeworks, well, 2 things. 1, homeworks need a cover sheet. You can make your own cover sheet. I don't care. Or there's going to be a cover sheet that's on Canvas. There's probably 10 to 12 homework assignments. You can go ahead and print off 10 or 12 copies of those, 3-punch hole them, put them in your notebook, and then you always have a cover sheet. The reason you need a cover sheet is because the other asinine thing that they taught you in freshman engineering is this concept of taking a homework assignment and folding it in half. Right? Do they still do that? Yes. Right? Which I understand, that's FERPA, right? So they don't want to see your name, they don't want to see your grade. What happens though, I have 50 homework assignments like this. I fold it, now I have 100 homework assignments there. I don't want that. I don't want to run around with that. So homeworks, stapled with a cover sheet on front. You'll see that the cover sheet that I have online has a spot for your signature, right? That signature simply indicates that you did not, quote unquote, cheat on the homework. Top bullet, very important. I feel like this comes up in emails a lot, emails that do not get responded to. Professor Davis, do you post solutions to homeworks? No, I don't, right? Because if I did, one, I've never seen it to actually be super helpful. Two, people wait to the last minute, you copy down a bunch of homework and you think that's gonna help you. And three, it causes me to constantly have to come up with new homework problems. Right? None of those are good. So I do not post solutions. Does that mean that I will not work through problems with you? No, of course not. Right? That's what office hours are for. That's what appointments are for. That's what, hey, on that last homework assignment, you asked this particular thing. Would you mind quickly going over that? Right? Those are times to get answers to homework solutions. I will post homework answers. So you know on number 2, I should have gotten negative 250 kilojoules per mole Kelvin. And you'll know, okay, I got that. So my solution is good. If you don't get that, and you don't know why you didn't get that, the office hours, come talk to me. Let's work through that. All right, so all I really have to say about academic integrity is we all know what it is. There's a number of ways to describe it, but the best way that I like to think about it is when you go to do something, just think about if you wake up in the morning and you're like, man, I'm thirsty. I'm gonna go get some orange juice. You go downstairs and you pour your orange juice drink. And nowhere during that process did you think to yourself, should I be doing this? Well, maybe, I don't know if you're diabetic, then that's a little bit, but you don't ever have that thought. But if you're ever working on something, you're looking at solutions, you're working with someone else, and you start to, yes, you should stop. Like that's when you know that you are crossing that line. Right, there is the obvious blatant copying, right, which is easily recognized and will be caught. Right, you can be really good about how you cheat. That's fine. Again, you can do what you feel like you need to do to get through this course. If you would like to work really, really hard to cheat your way to getting 9.5 out of 10 points on that, only to then not really understand 78 points of the course, be my guest, right? So just don't cheat. It's not worth it. I promise you, it's not. Even a 0 on an exam is, well, I mean, at that point, I guess, no. Even a 0 is better than cheating, because if you cheat and you get caught, that's on your record, you get kicked out of school. And you still get a 0. There's just no benefits to it. Right? Which means ask questions in class, right? So I know it can be hard sometimes, right? Depending on what type of person you are. Maybe you're introverted, you don't like speaking up in class. I totally understand that, right? The issue is that no one else takes the exams except you, right? And no one is standing over your shoulder while you're taking that exam, judging you, right? And no one is really, and if they are, I promise you, this is much more on them than it is on you. No one is leaving this class and for hours later saying, man, Allison asked that question. Holy what a moron. Like, No. And if they are, then that's on them. What the hell are they doing? Wasting their time thinking about some question you asked in class. You are here to better yourself, right? Make sure you are taking all the opportunities to, excuse me, to do that. The only other important thing is related to testing accommodations. If you have any type of testing accommodations, right, that's not something that you need to come talk to me about in class or after class, right? But just make sure that those are taken care of before the first exam. Okay. Are there any questions about anything we've gone over related to the syllabus? Yes.
Do you have exam dates for like midterms?
No, is the short answer. A little bit more detailed answer is second week of July, fourth week of July. Somewhere in there, yeah. Yes.
Will we be learning new material all the way up until that Friday date for the final exam? Like, in other words, will we be
Correct. Yes, yes. So then you will there will definitely be material that will not be on the second midterm that will be on the final exam.
Well, will there be like I guess I was trying to see like if material was going to stop like the Thursday before that Friday or like the Monday before that Friday for study time.
I see what you're saying. There's got to be something on the academic calendar about that I don't want to say one way or the other, but I feel like there might be something on the calendar about that. What is the last date I can actually like teach in class? But no, I mean, I think that, you know, the scenario I would imagine there, let's say it was, I could teach all the way up to Thursday or something like that. Then the scenario there, what we will end up doing very last is reaction equilibrium, right? And so maybe we, you know, spend a bunch of time talking about doing reaction equilibrium in the gas phase, and you get all these expressions for activity. This makes sense. You know, activity for these different gas phases. And then on that last day, maybe we talk about, you know, solids or liquids. And in that case, the activity of a solid or liquid is 1. And so I'm not asking you, it's not a far stretch, right? Like I'm not asking you to learn a new concept other than it's more of a simplification than what you would have learned already. Yeah. Yes.
Will there be like answers or solutions to the pressure?
Will there be answers? There will be, I will go over the refresher quiz. Yes. I will go over the refresher quiz. I will go over the exams. Feel free to copy all that stuff down. When I go over homework problems during class, feel free to copy that stuff down. I'm happy to work through it, right? But what I'm not going to do is like, here's the solutions to number 5 on homework 4, and just like, here they are, copy them down. All right, we're going to talk about them. Right, that is a little bit more time consuming on my end. That's fine. I would rather you learn the material than spend a bunch of time writing it down, and it just doesn't. You might as well do what you did back in elementary school when you had to write like 1,000 sentences, and so instead of writing like "I will not talk in class," you would do like I will, right? You're not learning anything. Okay, any other questions? Okay. Oh, one thing I always forget to put on the syllabus, and I say it every year. At least one homework you can drop. Like I said, there'll be 10 to 12. You can drop your lowest homework. If there may be some incentive program or something during the next month that would maybe allow you to drop a second homework or something like that. But for sure, at least one homework you can drop. Okay. No other questions? Let's get started. So if it wasn't clear from my email, on Canvas, you will find a folder that says lecture notes. Inside that folder, there will be various lecture notes that are labeled as blank. Those are fill in the blank, right, course pack lecture notes. You're expected to print those off before class. If for some reason I've gotten behind and I haven't been able to put something up on Canvas, I think in my email by 8 a.m. the morning of, then I'll print off enough copies and bring it and hand it out, right, in class. Maybe it would be good to take a note now of 1, 2, 6. So it looks maybe like 6 of you are using tablets. Is that going to be a pretty constant thing? That'll save me on having to maybe print out 6 things. That if you forget your tablet, you need one, I can always print more, but these should be up online. Again, the lecture notes are just more of a numbering, not lecture note 1 is day 1, lecture note 2 is day 2. That's just the order in which we're going to go through them, and we're just going to go through them. And if you don't have questions, we'll plow through a lot of stuff, and there'll be a lot of equations, and your brain will feel pretty scrambled by the end of this, right? So I encourage you to participate in class by asking questions. If you feel lost, enunciate correctly. 1, because that's helpful to you. 2, it breaks up the monotony of thermo. I'm going to try to be as energetic as possible when talking about the vapor liquid equilibrium between ethanol and water, but there's only so much, right, one can do. Highlights from the syllabus, we just went through all that. There are your textbooks. And so the first thing I want to do, right, is go over a brief timeline of thermodynamics in general. Right, so thermodynamics didn't always start off as we think about it today. It initially started off, right, with the study of temperature, pressure, and volume, right? And this initially started in 1662 when Robert Boyle published, whatever the word you want to use, Boyle's Law, which just said that pressure times volume was constant. Right, then we move along. Jacques Charles in 1780 discovered something similar, that volume divided by temperature was constant. He actually didn't publish that work, but later on, right, Joseph Louis, I'm not going to try to pronounce the last name, right? He came up with another law, which was pressure divided by temperature was constant, but he also verified what Charles found, which was that volume divided by temperature was constant, and credited him with such, right, which is somewhat rare in the field of science. Okay, later on, around 1835, is when we get what we know today is the ideal gas law. Right, all of those relations were combined by Clapeyron into the equation of the ideal gas law. Right, the issue here is that everything we've talked about so far only applies to gases. And there's these 2 other important phases that we care about, and so they knew hey, there's something that we're missing here. And so if we go back a little bit, in 1702, I'm not going to try that name. This person here posited what absolute zero was. They posited negative 400 degrees Fahrenheit. You can see that was actually very, very close to what absolute zero is. And that was later named the third law of thermodynamics, right? Which defines absolute zero. Then in 1749, Emile Chatelet maybe, for the first time derived the conservation of energy. This is the person who came up with the first law of thermodynamics. Right? So two things are crazy about that. One, you probably never heard of this person. Why? Because it was 1749 and she was a female. Right? That was an issue. Second crazy thing. This was done as commentary in the margins while she was translating Newton's book into French. So she was taking Newton's book, she was translating that into French. And while she did that, she also derived the first law of thermodynamics. Again, unfortunately, she was a female, so it wasn't until about 100 years later that this guy, Hermann von Helmholtz, which you have heard of, is credited with developing the first law of thermodynamics. And back in the 1820s, Sadi Carnot laid the groundwork for the second law of thermodynamics that was officially minted as the second law of thermodynamics when Clausius introduced the idea of entropy in 1850. And so now we have first, second, and third laws of thermodynamics. We also may or may not know that there is a zeroth law of thermodynamics. How many people know that there are 4 laws of thermodynamics? Okay, that's reasonable. Right. Why it's called the zeroth law? Well, that's just because when they decided or figured this out, they were like, oh, actually, this is the most important one, so it should be first. But we've already got it first. So then it has to be the zeroth. And that is just simply that all energy, right, ceases at thermal equilibrium. Right? And it's, I guess, what you would call the law of thermodynamics that defines thermometers. That's how a thermometer works, right? Energy flows either in or out of the system at thermal equilibrium. There is no energy flow because I have a constant temperature. The last one that's really important for us is this guy Gibbs, right? In 1875, he published his general principles governing thermodynamic equilibrium. And this is what the vast majority of this course is built on. I also included Boltzmann there because that is a monster name in the field of stat mechs, right? Which his famous law to describe the entropy based on the number of available states. That law was so important that it's actually engraved on his tombstone. Okay, so what's really nice about everything we talked about after the first slide is that all 4 of these laws, really 3 that we care about, define or govern all material, right? Not just gases. And so when we think about thermodynamics, right, let's make sure that we have our language down. Because again, if we get lost, you don't pay attention, you're going to come in here in a week and you might as well be sitting in advanced Chinese. It's not going to make any sense to you, right? So please, let's make sure we get the language down now. So when we think about thermodynamics, we typically think about the universe. Within that universe, we can define a system, right? And that system is typically divided by what is part of our system, surrounded by some boundary, and that boundary separates our system from the surroundings. Right? We can have interactions between the system and surroundings. One of those can be heat. Another one could be work, right? One example of work might be shaft work. I might also have some expansion or compressive work that I do on my system. When we think about thermodynamic functions, we ask ourselves whether that is a state function or a path function. A state function being something that all I care about is the initial and final state. I don't care how I got there. What's an example of a state function? Enthalpy, entropy, internal energy. So what's a path function? We have 2 main path functions that we think about our first law. We have energy, yes, work, heat. Right? Yes, it matters whether or not I take 100 small steps in some direction to get up 10 feet, or I take that same amount of weight and I lift it straight up 10 feet. Like that work is different. The path that I got there was different, even though I got to the same place. Okay, state functions, yeah, just think about your typical thermodynamic properties. Enthalpy, entropy, Gibbs, internal energy, path functions, heat, work. Equilibrium, we have 3 types of equilibrium. Thermal, our temperatures are equal. So I can have mechanical. For us, we think about mechanical in terms of pressure. Right. And then chemical, we'll talk about here short. I can write that in a number of ways. I'll write it by saying that the chemical potential in one phase is equal to the chemical potential in the other. Processes, they are all real processes are irreversible, right? But sometimes solving something in a reversible manner gives us helpful information. All right, and then we have either steady state or unsteady state transient processes. All right, for this course, this document is very helpful. What you see there is a general system property. That means that can be this, that can be that, that can be that. That can be that. A general thermodynamic property. I'm not talking about temperature. I'm not talking about volume. If I have an underbar, that's a molar property. This is the molar enthalpy, the molar entropy, the molar internal energy, and the molar Gibbs free energy. If I have some system, right, it has a number of components, then that is the enthalpy of that component in that system. So maybe here, that's the enthalpy of H2O. That pure component can also have a molar enthalpy. Right, so again, we're not talking about temperatures and pressures here, just so we are explicit. Right, we are talking about volume, right? We can't have molar volume. We can't have partial molar volume. You can have a partial pressure too, but then we'll talk about that. That's different. All right, so just make sure that if you ever have a question about what property is being given to you, right, or what units go with that property, the best way to know is, does it have a bar? If it's got a bar, it's got to be per mole. I don't care if the bar is above the letter, or excuse me, I did that backwards. I don't care if the bar is above the letter or below the letter. If it's above, it's a partial molar volume. So this is a partial molar volume of water. That is the molar volume of water. Do they have the same units? Of course, they're both molar volumes. You'll see IG for ideal gas, IgM, ideal gas mixture, IM, ideal mixture. We'll talk about excess properties. All right, the other big one that I think people get confused with are these last two. If I say to calculate the enthalpy change upon mixing 1 liter of ethanol with 1 liter of water, that's what I'm asking you to calculate. Right? That is the change in enthalpy upon mixing, is a way to think about that. I could also just ask you for the enthalpy of a mixture of ethanol and water. That's what that is. So my mixture itself can have an enthalpy, but there can be some enthalpy change upon mixing. All of this will start to make more sense as we work through problems, but it's good that we go ahead and get this notation down at the beginning. Okay. So first law of thermo. We can write it in a number of different ways. Right, from Sandler, we can write out the full differential form, right, where I have the change in internal energy change in kinetic energy, change in potential energy. And so that's the delta energy of my system. I might have an open system, right? So I might have some mass that is entering or leaving. And then our other two terms. Of a rate, energy, or heat flow, and then the rate of which work is being done on the system, or the rate at which the system is doing work on the surroundings. Now here, this term includes both shaft work, right, and work done by a boundary. So both shaft work and our dV dt term. Right, the negative here comes from the convention, right, that we are doing work on our system when we're compressing it. The dV dt would be negative in that case. And our system is doing work on the surroundings when there is an expansion, where dV dt would be positive. All right, Q here, we just think about that like our bank account. Heat's flowing in, money's flowing in, positive, that's good. Heat's leaving, money's leaving our bank account, that's negative. Positive heat flow means that if I were to ask you how much heat needed to be added to or taken away from a system to ensure that it remains isothermal, you would need to know the sign of that. Is that process endothermic or exothermic? Am I going to have to chill it, or am I going to have to heat it up? Right, and like we already said, heat, work, path functions, internal energy, state function. Second law, that states that the entropy of the universe always increases for all irreversible processes and is equal to 0 for reversible ones. In a differential form, maybe it's open, we have some mass moving across the boundary. That Q dot divided by T term, that's our rate of entropy flow, right, based on heat flow. And then the S dot gen is the rate of internal entropy generation in our system. And I have some questions there that you can ask yourself. All right, so let us finish up with our review of Thermo 1 by talking about our FPRs, or fundamental property relations. We have 4 of them. Should you memorize these? It couldn't hurt. It's only 4 of them. Oh, exams. That reminds me, exams. All of the exams are closed book, closed notes. Right? Does that mean that you have to memorize these equations? These four, I would encourage you to. They're not that hard. Do you have to? No. Right? A week before the exam, so 7 days before an exam, I will post on Canvas an equation sheet. That way you have a week to look over that equation sheet, see what's on it. I'll take time. It'll be organized nicely for you. Right? Is it going to have every single equation that we go over in class? No. Will it have forms of equations that then you can use to derive the equation you need? Yes. Right? But you will know that beforehand. You'll say, oh, okay, he didn't give us the full form of this equation, but he gave us the integral form. All I know is I need to integrate from T1 to T2, and then I'll have the form that I need. The last one here, I've highlighted in red because that's the FPR that relates to Gibbs free energy. And we're going to find that that's going to be our important thermodynamic relation for this class. For Thermo 1, it was H and S. And for Thermo 2, it's going to be G. And we're going to be thinking about G in terms of H and S. Okay, and so to do that, if I take the second equation here, I'm going to rearrange that. And that's a negative. Then I'm going to take that, I'm going to put it into that bottom equation. The vast majority of the problems that we're solving are going to be systems that are in equilibrium. That means that the temperature, right, the pressure, and that chemical equilibrium that we talked about are all equal. Right, so most things for us, if I can write correctly, are going to be isothermal. And so really the important FPR for Gibbs I would argue is that equation. I get DH from the first law, I get DS from the second law. This is Thermo. If you ever feel like you don't know where to start, they literally named the laws for you. And you didn't even know about the zeroth law before, so just forget that. So start with the first and second laws. That's never a bad place to start. It's going to give you some information. You may find like, okay, I didn't actually need that. But you'll find that oftentimes you do need information from the first and second laws to solve problems. And then ultimately what we're going to find is that we need that information because what we really care about here is this Gibbs free energy. I can take any of these relations and put them on a molar basis, right? Meaning this top equation, I can just go in and do this. Now that's the FPR on a molar basis. And you can kind of think about that as the same as saying that the density of something is, 18, I don't know, pounds per pound mole, 18 grams per mole, right? It's all the same, right? I'm just changing the basis on which my units are. I'm doing the exact same thing here, right? One's extensive, one's intensive, but they're the exact same. All right, so let's solve a problem going back to Thermo 1. Which for some of us wasn't that long ago, right? It's spring. For others, it's maybe been a while since we've thought about Thermo 1. In this example problem, you are asked to calculate the change in entropy when 1 mole of saturated ethanol vapor condenses at its normal boiling point. You're told this process occurs isobarically and the pressure is 1 bar. I don't know why the properties aren't listed there, but here is some helpful information. And so let's imagine that's the problem we're given, and we're given this information. Some of you might look at that and think, oh man, not this again. But we're gonna, again, employ my method of when in doubt, write the first and second laws, okay? Here, we're gonna skip the first law because the problem tells us we can do that. Why? Because for right now, it's asking for the change in entropy. We may find out later that we need something from the first law, but let's just stick with the second law right now. I'm going to write it in a bit of a different form, but it is the same entropy balance that you saw on the previous slide. It's just now, instead of in a differential form, in an integral form. Again, same thing. Just now I have integral forms on the right-hand side, and I've already integrated the left-hand side from state 1 to state 2. Right, if you weren't told this, would I tell you this? Probably I would probably write the problem like this and then do it and then say it's fine and then last minute change it. And I would tell you to assume a reversible process. I would maybe naively hope that because of your experience in Thermo 1, you would recognize that a phase change of a pure component that occurs isobarically is essentially a reversible process. But let's say you didn't have that, and I said, okay, now assume this is a reversible process. How can I simplify my equation? Okay, I heard S gen equals 0. I agree with you. What's another safe assumption that one might make here, even though I'm not told? Steady state assumption. Yes, sure. I agree with you. Steady state. the term that I would probably add to this problem, or I would say assume closed system. And so I shouldn't have any mass moving across my boundaries. You might also, again, draw that conclusion. I'm asking you if something is condensing. Right? You shouldn't expect there to be mass moving in and out of my system. Right? And then the other part that I'm told is that it occurs isobarically. What's the implication of saying it occurs isobarically? Say that again. Say that one more time. Constant pressure. Yes, that's what isobaric means. What is the implication? That's a great answer to my question. That's the direct answer. What is the not direct implication of isobaric? If I tell you that I condense something isobarically, what also has to be true? Okay, if there's no change in volume, then what's true? There's no change in temperature. Right, so then what happens is that T pops out the integral. And then I'm simply left with the following equation. My Q dot was a rate of heat flow. I just integrated over time. So now it's just heat. Okay, now we look at this and we're gonna go a couple minutes over, I'm sorry. And we say, hey, look, that's the delta S you're asking for. But now I have an equation with Q in it. And you've given me a delta H. So what do? When in doubt, oh, I skipped over the first law. I probably need to go back to the first law. Right, so what I know is that at constant, can I spell? No. At constant pressure, dH equals Q. Right, how do I know that? Well, because dH equals du. Well, actually, I would write it like this. I would tell you H equals U plus PV. We've all seen that. Then I say D, right? Differential of all those. Bless you. For a closed system. I know that to be true. All right, so I chain rule, product, not chain rule, product rule, right? The last term, I'm going to end up with two terms. I'm going to end up with a VDP and a PDV. Well, I see my negative PDV cancels that out, right? I'm assuming constant pressure, so my DP term goes away. And so not many of you, I think, maybe appreciate why this is the case in these certain systems, but this is why I am able to say that du equals dH here. That's not always true. Right? It's true because I have constant pressure and I have a closed system. And because I can make those two things equal to each other, I can put that into that last equation. When I combine those two equations, right, I'm going to get that dH is equal to Q. Right, meaning that the reversible, right, energy here should be equal to my delta H. Right, the thing that I have to think about though is the delta H that I'm given. What am I given here? I'm given the change in enthalpy upon vaporization. I'm asking for the change in entropy upon condensation. So how is the change in enthalpy upon vaporization different from the change in enthalpy upon condensation? Just a sign difference. And so then this equation here just becomes negative delta H vape. The T here, well, we are told it occurs at 1 bar, and we are given the vapor pressure, the saturation temperature of ethanol at 1 bar. So then this is simply T sat. And then all of that would be equal to my change in entropy upon condensation. The math on that is trivial. I get a value of around negative 0.1097 kilojoules per mole K. Go back in, plug those numbers, confirm that to yourself. All right, is that okay that there was some entropy change in my system? Is that allowed? Does that violate the second law? Why doesn't it violate the second law? Yes, that is why the sign is negative. So if that's losing entropy, what's gaining entropy? The surroundings, right? And so my overall delta here is 0. Okay. This is a reversible process. And we know that for a reversible process, delta S for the universe has to be 0, not for our system. So yes, this would be the delta S of our system. And then if I said, hey, tell me what the delta S of the surroundings are, you would just come back and put a positive in front of that. All right, are there any questions about that example problem? Okay, if not, I'm going to stop there. I've gone over 5 minutes. I'll give you those 5 minutes back at some point during the summer. But we will pick up on the last 2 pages and start talking about the material for Thermo 2. Right, again, you're going to find the refresher quiz study guide on Canvas. I encourage you to start looking through that. Right, making sure that you understand how to solve or answer all 22 of those items, right, on the study guide. Right, the first one is like, it's got like 15 terms in it that are terms you should know, right? It's not like you need to pull out flashcards and no, just like work, adiabatic, reversible, right? Just make sure you know these terms so that if it comes up on a refresher quiz, you're not like, what the heck does he mean by reversible? What is shaft work? Okay, awesome. Well, it's nice meeting everyone. Sorry we were delayed starting today, but see everyone tomorrow at 1:30. Yes.